Hey, so this is Joseph, and this is the video for the first part of the second chapter of Stewart's calculus. And we're going to be talking about the definition of a derivative. So derivative is a rate of change. And as you might remember earlier on in the book, we were talking a little bit about finding the slope of a line that lies tangent to a curve, or instantaneous velocity, and both of those are rates, and they're instantaneous rates, and that's what a derivative is. It's the instantaneous rate of change of something for a single point. And now that might seem really nebulous, but now that we have talked about limits and you know about limits, we will be able to kind of show a practical application of the derivative and also kind of practically define what a derivative is, and I think it will make a little bit more sense as we go along. So let's go back to something that might look a little bit familiar. We're going to try to find the rate of change, or the slope of a line that lies tangent to a curve. Alright, so here we've got the curve y equals negative x squared plus 3, and we're going to try to find the slope of the line that lies tangent to this curve y at x equals 1. And so x equals 1 is going to be right there. And as we did earlier on in the book, in this video series, we're going to first try to approximate that slope by finding the slope of the line that passes through x equals 0 and x equals 1 on this curve. And so you see x equals 0, when you plug that into the function, equals 3. X equals 1, when you plug that into the function, it equals 2. And so that line that passes through those 2 points is y equals negative x plus 3. And how do we find that slope? Well, we can use this nice and handy formula here. M for slope is equal to f of a minus f of b over a minus b. And it doesn't really matter what order a and b come in. Here it just matters that the a's line up and the b's line up. And so in this case, our a is 1 and our b is 0, and so this means you plug 1 into the function and you get 2 minus 3, so it's negative 3, and then you get 1 minus 0, and that's 1, and so we get the slope ends up being a slope of negative 1. And that's reflected in the line that passes through those two. The slope is negative 1, and then that plus 3 is the y-intercept, and the y-intercept is 3 because the function at 0 is 3. So that makes sense. And now remember what this, and so if we're trying to find the slope of the line that it lies tangent to the curve at x equals 1, which is right there, what we need to do is make the difference between a and b really, 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 really small. And how do we get stuff really, really small like that? Well, we can use a limit to make one of these values approach something. Specifically, what we can do is this. Use this limit. The limit as x approaches a, f of x minus so x is any point on the x-axis, and a is the point that we're trying to find the slope of the tangent line at. So in our case, a is going to be equal to 1, and x is any point on the x-axis. And so this bit of the formula right here, that looks exactly like our slope formula. We have the function of something minus the function of something else, minus that first something minus that something else. However, here we're making x approach a. So that the difference between x and a is getting really small. It's going to be the smallest it could possibly be, to the point where essentially it's the same point because x is actually approaching a. Now if we were to use the plug-in method, that's a method I was talking about earlier, and just put a in for x, we'd get a 0 into the denominator, and this would be undefined. However, let's just give this a shot at solving. Alright, so what we can do is, let's just write out that limit again. Alright, so now we can apply this to that function negative x squared plus 3. So that will equal the limit as x approaches 1, because in this case a is 1, of f of x minus f of 1, x minus 1. So, and now really make it apply to that function. Remember, the limit has to come down every time on the AP. If you don't bring this little limit talk down each time when you're doing an equation like this, they will mark it wrong. So we got negative x squared plus 3, and so plus 1 minus 3, because that's a minus sign right there, x minus 1. So now we can do some canceling. The 3's cancel, and we've got negative x squared plus 1 for x minus 1. So the problem with this limit right here is, unless we use the method that we'll learn later on in the book that actually involves using derivatives, we can't solve this limit. I don't know really how to distribute that function without using square roots, and this doesn't cancel. So we've come to a little bit of an impasse. Although this limit does exist, we will be able to solve this. We can't right now, and not with this sort of notation. So although this is one definition for the derivative, let's try to pick a better one that will make limits easier to solve, and we can actually do that relatively easily. Okay, so we're going to keep the same kind of talk as we did earlier, where x equals 1, that is a. However, instead of using another variable x, what we're going to use is a variable for the distance between a and any other point on the graph. So using this slope right here, let's just call, x 0 for the moment, but really it represents any point on this axis, and the distance between the two, h. And so ultimately our goal here, and with the previous definition of the derivative that I gave earlier, when we make this x approach a, this distance, this h, is approaching 0. Well, can't we write out that limit where we just have h and actually put that explicitly in the function, make that h approach 0? Well, yes, and this is actually the more commonly cited definition of the derivative, and we can write it out like this. The limit is h approaches 0, the function of a, so in this case 1, with this graph, a plus h, and so that is kind of a placeholder for what previously was x. X would actually be a minus h, but h would be a negative number. So a plus h minus f of a, same as before. And then if we were directly substituting this in for the previous definition, it would be a plus h minus a, but really that all just ends up being h. So this is the most common definition of the derivative. And now let's try to solve for the instantaneous rate of change, or the derivative, or the slope of the line that lies tangent to this graph at a equals 1. So we've got our limit. Now let's apply this to the function. Actually make it super apply to the function. Limit as h approaches 0 of negative 1 plus h, because remember we're just going to be substituting this a plus h, this 1 plus h, in for x in the function. Squared minus 3, and then remember f of 1 is 2, so we've got a minus 2 in there. Sorry, that should be a plus over h. Now let's distribute this little polynomial right there. Now we can start canceling out some h's to get this h out of the denominator, because that's ultimately our goal here. Because would we use the plug-in method, we would get a 0 in the denominator, and this would be an undefined limit. However, we can try to get this h out, and we will be able to, as you will see. Aha, and now, since we have two h's here, we can factor one out, so that it's so these h's will cancel, and we will get the limit as h approaches 0 of negative h minus 2, and now we can plug the 0 in, and we will get a negative 2 as the limit, this limit, or the derivative of that parabola at 1, at x equals 1, is negative 2, the rate of change, or the slope of the tangent line to the graph. And so let's see that graphically here. And so we see that the line with the slope negative 2, and you plug that then into the y equals mx plus b, the standard form of a line function, and you get the y-intercept as being 4. That line lies tangent to the graph, and thus is the derivative, and that limit shown previously is the definition of a derivative. So, to prove to you and kind of illustrate that derivatives don't just represent a slope of a line that lies tangent to a function and is just generally a rate of change, I will show how the derivative is applicable to sort of physics problems using displacement, velocity, and acceleration. So displacement, which can be written as change in x, or commonly in physics and in math, change in s. I don't know why they use s, they just use s. Displacement is the amount by which something's position changes. So if I'm at driving my car and I drive 1 mile, my displacement is 1 mile. And displacement factors in positive and negative distances. So say I drive 5 miles to work and then drive backwards another 2 miles to get lunch and then forwards 2 miles. I've still only driven, my displacement has only been 5 miles from my point A, my home, and then point B, my work, even though there's that negative 2 plus 2 miles in the middle there. And that's not really important right now, but that will be important later, and so it's just good for you to keep that in mind. Now, velocity, on the other hand, which is v, is the displacement over time, so the change in position over change in time. So it's basically the amount of time. You can look at it as how much time it'll take you to go a certain distance, and that's kind of how fast you're moving. And so when we have these two little changes here, velocity can often be a slope of a position function as a function of time. So say you have a position function s of t equals x squared. Velocity, or average velocity, is a slope, the slope of a line that passes through 2 points of this graph, and that's an average velocity. However, what if we want an instantaneous velocity, like we were talking about? Well, then you have to use the derivative. And in this case, the derivative would be the following limit. And as we're looking for instantaneous velocity, we want this change in s to be really small. We want that change in s to approach 0. And so that's why we're using the derivative. And we're going to be, and so the velocity we can express as the limit as t approaches a, and we're using t instead of x, because when you use displacement problems, the displacement is generally in terms of time, until we get into multivariable calculus, in which case it can be different. You can have different parameters, but it will be s of t minus s of a over t minus a. And we see this is the first definition of the derivative. And so it can also be expressed as the limit as h approaches 0 of f of a plus h minus f of a over h. And so velocity really just equals the derivative of the displacement. And that little prime there shows that that's the derivative of s. And we've got the same thing with acceleration, and I won't prove it to you here, but acceleration is basically the change in your speed. And we can use the same process to show that acceleration equals the derivative of velocity. And when you take the derivative of one thing twice, it's called the second derivative. It's really just taking the derivative of the derivative. And so that would mean that acceleration is also equal to the second derivative. We express this with 2 primes of displacement. A little t there to show that these are functions. And I'll show you later that you can't take the derivative of a whole function, which is actually what I'm going to do right now. Alright, so now taking the derivative of a whole function and getting another function back is basically saying, alright, I've got this function, in this case y equals x cubed, and I want to have a function that maps the instantaneous slope of every line tangent to this graph to every value of x. So basically the derivative curve is going to be a curve of all the slopes of all the tangent lines of this curve, or all the rates of change of this curve. And so generally, let's just remember all back to the very basics that the average, like, you can express that derivative as the change in y over the change in x, so long as that change in x is super small. Those x's are really close. In other words, this would be the limit as the change in x approaches 0 of the change in y over the change in x. And so when that change in x is approaching 0, instead of writing out this limit every time, what we can just do is change those deltas into d's, dy over dx. And so that means that this is the derivative. That's the super small change in y over the super small change in x right here. So, and it's so small that that change in x is actually approaching 0. And this generally represents a function. This represents the derivative function of this, and we can put in here a little, little x. Or actually, you don't even need to do that because that's redundant to this change in x. So there's your notation for you, and also a little bit of concepts. And now let's return to the definition of the derivative. So we've got dy dx equals, the limit as h approaches 0 of f of a plus h minus f of a over h. Now, we're not just trying to find the derivative at a certain value a, so this equality is kind of wrong. We're trying to find it for all values x. So instead of writing these little a's in here, we're going to write an x, representing the whole set of all these values. So this means that once we solve this for x, we're going to get a function with x in it, and a curve will come out of that. So let's try to find this for the curve y equals x cubed. We can do that right here. So we've got our definition of the derivative of a whole function, the limit as h approaches 0, f of x plus h minus f of x over h, and we will apply this to our function, which is h, and so that's going to be x plus h cubed minus x cubed over h. And now we're going to have to distribute this nasty cube, and I already did it for you on paper. You can check my math if you want, but that will end up being a long old polynomial here, x cubed plus 3x squared h plus 3x x. So remember, our goal here is to get rid of that h in the denominator, because when we plug 0 in for that, we get an undefined function. And so we see that these x cubes cancel out, and we can combine, or we can't combine stuff there, but we'll be able to take some stuff out there. In fact, actually we will take some stuff out. We can take one h out, which will give us 3 x squared plus 3xh plus h squared over h, and lo and behold, these two h's will cancel, leaving us with when we plug in 0 here, these two terms will go away, and we are left with 3x squared. So this means that the derivative of that function y(x cubed) is equal to 3x squared. And now let's show that graphically. We can do that right over here. There you go, 3x squared. There is that graph. And I'll prove to you that each of these values represents a slope right here. So let's find the tangent line to the curve, x cubed at x equals 1 is 3x minus 2, so we got a slope of 3, and at point 1, which is right here, we get point 3. Boom. That derivative curve is the curve of all of the slopes of all of the instantaneous lines on this function. So that's the definition of the derivative. I hope that that's helpful, and stay tuned for the rest of Chapter 2. It's definitely an interesting one.